Good afternoon. I'm Lily from Singapore Water Association. Thank you for attending today's webinar call organized by Singapore Water Association and George Fisher. Today, we will start with a welcome address by Mr. Antoine Walter, Senior Business Development Manager, Wastewater Treatment of GF Piping System HQ. We are glad to have Mr. Antoine Walter to speak on what if underestimating sturdy sensor inputs actually prevented you from saving big on energy. Then we will have a 10-minute Q&A segment before we end the session. Before we proceed, I would like to touch on some housekeeping rules and disclaimer clauses. To ensure better connectivity, please mute your microphone and turn off the camera. You may communicate with us after the event. Please share your questions in the chat where we will try to provide answers where possible in the Q&A segment. Do identify yourself so we can respond to any unanswered questions. We'll be recording this session and reserve the right to the video. To complete an event survey, which upon return we will forward the recording and presentation deck to the respondent. All information shared is for general information only and does not contain or convey any legal advice or administrative assistance. Information shared today is true and accurate as of publication date. The organizer and the speaker reserve all right in the provided materials. So without further ado, may I invite Mr. Antoine Walter of George Fisher to give us the welcome address and presentation. Mr. Walter, please.
Hi, everyone. Welcome from my side as well. Thanks a lot for being there this morning on my end of the world and this afternoon for you. Thanks to the Singapore Water Association for welcoming us here on that stage and to enable us to discuss this, I guess, interesting topic, I hope for you as well. I will be co-presenting and co-hosting this webinar with my colleague, Christine Yap, who will be collecting you from the chat. Hi, Christine. So if there's any question.
Hi, Antoine.
If there's any question during the webinar, please raise them in the chat. We'll be very glad to answer them. Christine will be hosting the Q&A at the end, and she will be also your interlocutor if you have follow-up questions after this event. That being said, very short about me, you might notice from my accent that I'm French. I'm sorry, nobody's perfect. And I will have the pleasure to tell you a bit about a project that might happen. Sorry, I shall be back in a second. I'm back. About a project we were conducting last year, which was a bit slowed down and changed a bit by the pandemic, like all the projects were, but I think we have some very interesting outcome. And with that presentation, I'm going to switch to the actual content of that webinar. And you shall be able to see my screen in just a second. I think you are right now. Good. So our topic today is, it's about optimizing operation if you're running a plant, if you're running a wastewater treatment plant, but in general, if you're running a plant. And why is it important to optimize your operation? Well, actually, for a very simple reason, is that if there's one thing that we try to avoid as water professional, usually it's to make the news. Let me here share you something that happened very recently in the UK. It's a story of two wastewater treatment plants that, unfortunately for them, made the news because they were leaking untreated wastewater into the rivers. And not just once, they found out that those two wastewater treatment plants had been leaking sewage for the past decades, approximately 1,000 times. And actually, the operators of those plants never noticed that they were doing that. So they didn't do it on purpose. It just happened. And the way to detect that was actually to use artificial intelligence. And it was a study done afterwards by some scientists in the UK to check on those plants and to see if there was some spillage. And let's see what actually happened. What actually happened is that those plants were very well operated. So it's not about shaming the operators. And the UK is a highly regulated country. So it's not like nobody would care. But if you're not looking at the right place, there's almost no chance for you to detect something which is outside of your focus. What machine learning enabled on those plants is actually to have a look at the curve you see here on the slide. You see the blue curve. The blue curve is what is expected to happen in the plant in normal conditions. And the black curve is actually what happened when the spillage was occurring. And what you see here is that the black curve is flat or almost flat, whereas the blue curve has all these nice curves actually. And if you're not looking at that pattern, there's almost no chance for you to detect that something is happening. But what you see just beneath is that this spillage was occurring on these approximately 1,000 times, but not over 2 minutes. Sometimes it lasted 3 days where there was just spilling untreated raw wastewater. And that is, of course, something you want to avoid. So if you want to avoid that, we can raise that question. Could operators detect such events? And I mean, you've seen the slide. Of course you can. Have a look at the graphs. You clearly see that the black curve is flat and the blue curve is curvy. So if you see that, yes, you can detect it. But wait a minute. First, you have to be expecting spillage, because if you're not expecting the curve to be flat, you're just not looking at the curve and you're just not checking if something is happening. And the second thing is that you have to know where to watch, because right now I've showed you the curve which allows you to detect something. But if you don't see that curve and you see the other 100 or 1,000 curves you might be able to see as an operator, well, it's difficult to know that something is happening. And actually, you have to have time to dedicate to that, because you might be greasing a pump. You might be just checking on the operation of your plant and not watching some curves. And finally, you need to know which pattern is the one that you shall detect. Because here I told you that the flat curve is the pattern, but had I told you that the pattern you're looking for is some peaks, well, you just don't see some peaks here on the curves. So that is something which also introduces a new element, because the patterns might change. You know, when I was in engineering school, everybody was telling me it's very simple to look at patterns. At 7 in the morning, there's a peak. At 7 in the evening, there's a peak, because people wake up, take a shower, go to work, come back, and take another shower or go and pee. So that gives you the usual pattern. But for now, 1 year, and you can see that from my background as well, we're all at homes, which means that the patterns are moving. And here you see that within 3 weeks in the city of Karlsruhe, they were noticing that the patterns changed because the behavior of the people because of the pandemic changed. So here, if you're an operator, you're looking at a pattern because you want to avoid anything to happen in your plant, and on top of that, the pattern changes. What I'm trying to tell you here, it's very simple, is that yes, you can detect a lot of things as an operator within a plant, but that goes at the bottom of it far beyond the capabilities of any kind of human brain, just because there's much data and far too much data to process for you to make an intelligent understanding of this data. So you need some help, and that help can actually come from machine learning, IoT, artificial intelligence, and that's what we're going to say, what we're going to see together today. So now let's park that for a second, and let's look at big data, because you might think on the other end, well, big data is something crazy. Look at Spotify. Spotify has 20% of the songs which are uploaded to that platform, which have never, over the course of almost 20 years, never been listened to. So that data is there and it has never been used. Then there's this very, very little social network, which is called Bourbon, and which enables you to check in at some locations. And it has so many features, like 20 features. And one of these 20 features is that you can take some pictures and share those pictures. But it's just one of the 20 features. But it turned out that actually that feature was the one that people loved. So Bourbon changed its name and was then called Instagram. And you may know that it's the second biggest social media nowadays. So they developed many things, and from that many thing, the only thing that sticked was this picture function. And finally, there's this very, very little website called YouTube. And YouTube was built to be a video dating site, not at all the YouTube we know today. So what I'm trying to tell you here is that you cannot know for sure today which data, which feature is going to stick, which one is the one that is going to be useful, that is going to help you in the future. But if you're not starting, you have no chance to leverage this data one day. So the important thing here is to start working with data and to cope with the uncertainty of future and to shape it. So that is what we will be exploring today, and that is what's our vehicle to improve the operation of our plants. And to have a look at what we shall improve, let's look at the way a plant is running today. So let's say you're the operator of a wastewater treatment plant. Today, you have one single step in your full process, which is eating at least 60% of your energy. And that single step is the biological step, be it a membrane bioreactor or an activated sludge process or any kind of other biological treatment step you may have. That step is consuming 67% of your energy if you are a small plant, namely an industrial wastewater treatment plant, and is eating 60% of your energy if you're a bigger plant, so most of the time a municipal utility and a municipal wastewater treatment plant. So that is for sure an area of interest if you want to reach these targets that many countries have set, and the leading one being Singapore, to reach one day a net energy positive wastewater treatment plant. Because when you think of it, a wastewater treatment plant comes with heat, comes with organic content, comes with resources that can be leveraged to produce energy. So it could be possible at some point to reach this balance and to outreach the balance and come to a net positive plant. But that starts by not wasting too much energy on some certain specific process steps. And why actually do we consume so much energy on the biological treatment? Well, because we use a combination of throttle. We look at the mixed liquor suspended solids. If they are too high, if they exceed the intended threshold, well, you pump up the aeration, you push the turbo mode, and they go down. But when they go down, at some points, they end up being too low, so you brake. And when you brake, the MLSS go up again, and you can have again this situation where they are too high. So what do? Well, you repeat. And that sounds crazy when you look at it like that, but that is happening every day in every wastewater treatment plant in the world. It's this combination of one day turbo mode, one day slow, one day turbo mode, one day slow, which means you are never operating at the optimum. And why is that happening? That's happening because we have a hard time nowadays to understand where we stand in terms of organic loads. It is very hard to predict. It's very hard to understand where this organic load is located when it comes to the secondary treatment, when it comes to this biological step. And that is really difficult as an operator, because if you don't have a clear sight of what's happening within your network and within your plant, well, you have no chance to do better than what you do today. So let's look at a very, very simplified way to underline that problem. And that is actually this representation of a network. Don't worry, I know that there's no network in the world which is that simple, but here, just to make it simple, I made it schematic. So on the right hand, you have the wastewater treatment plant, and on the left hand, you have the network. So in my network, there's 2 industries and 2 residential areas. In the real life, there are thousands of them. But you're going to see that even with these 2 and 2, it's already difficult. And even with this only 4-step on the right hand, it's going to be difficult. Why is it difficult? Because today, where do we measure organic load? We measure it at the inlet of the plant. So at that point, you measure everything. And then we measure it a second time. It's the outlet of the plant. So hopefully, with this point at the inlet, you get sufficient data so that your plant treats everything to the expected level, so that by the outlet, you are in within your allowance and you reach your expected treatment target, and you don't have to stop discharging or to take a fine or to be in trouble. But that is still wishful thinking, because actually what you're looking at with that single measurement point at the entry of the wastewater treatment plant is actually this. It is a speed trap. You might be running at 130 kilometers per hour by the entry, and it should be limited at 50. Well, good. But what happens? I mean, you're far too fast, which means you are far too high with your organic load. And the wall is just beneath, because the secondary treatment is maybe 3 minutes of hydraulic retention time ahead from this measurement point. But you have no way to brake. You have no way to do anything about that. So basically here, everything that this indication gives you is, hey, you're going to be in trouble. So what do? You push the turbo mode. And then maybe the next day, by the entry of the plant, you're at 10 instead of 50 and say, hey, too low, I'm going to brake. So that measuring point is not helping you, or not much. And that's only one problem. The second problem is that that measurement point is happening at very best once per hour, because someone is taking a sample, taking that sample to the lab, measuring and analyzing around the sample in the lab, and giving you a result. And in some plants, it's once per hour. In most of the plants worldwide, it's once per day. The problem is, we as humans, we have a hard time dealing with single points, because when we see single points, our brain is building the story around it and saying, hey, it's not just points, I'm seeing the trend. And you end up like that. Like you're looking at those points and you say, hey, I see a bear. I don't know for you, but personally, when I was looking at the sky, I never saw the bear. So it was like, to me, it's just points. If you translate that to the wastewater treatment plant, you see those points, and you see that yesterday I was at 10, and today I'm at 100. So you draw a line, and you expect tomorrow to be at 200. But maybe within the night, you were at 200, and when you see that 100 is already down, but you don't know. I mean, you don't see the trend, so you don't expect the trend, so you just don't understand what's happening. All of that to say that there was a study done on wastewater treatment plant operators in 3 countries, Switzerland, Israel, and Germany, and they were asked, how often, according to you, does the state of your inflow change? And they answered, well, on average, once a month. So they detected as operators once per month that the quality of the water was changing. And in fact, when making in-depth analysis on those same plants, what the study was showing is that actually those changes in states were happening 3 to 4 times per week, which means that it's almost once per day, and the operators notice it once per month. There's a strong discrepancy between both, and it's hard to stay with this best possible proxy of this one single picture, one single speed trap at the entry, because you're missing so much on information. So what do? You keep doing throttle and brake, and you spend 60% of your energy on that throttle and brake. So that leads us to a very simple question. Is there a better way? Well, I'm working for a sensor company, GF Piping Systems, so of course there's a better way. Let's put water quality sensors everywhere. And that's a good news for us. We're going to sell much more sensors, because it sounds about logical. To better monitor the organic loads, we could add sensors everywhere in the plant and everywhere in the network. But that leads me to a question. How many do you need? Do you need 10? Do you need 100? Do you need 1,000? Is there a limit? Shall you put sensors everywhere? That's already something which we would have to answer. And the second question is, how much would it cost? Because an advanced sensor which is measuring organic load, is relying on advanced technology, and there is a direct link between a technology and its cost. So if you start putting 1,000 organic sensors in your networks, it's probably a good news for Christine and me, because you're going to buy so much sensors, but probably for you, it's not sustainable on the long run. And another reason why it's not sustainable is because it's probably not very accurate over time. Because if you start putting many sensors at many different places, it's hard for you to watch those sensors closely. And if you don't watch them closely, they might be drifting and you're not noticing. They might be up for maintenance. They might be up for many different things, but you don't watch it close enough to notice that that drift is going to bring you in trouble. And what now if it turns out that after having installed all these sensors in the network, you're not monitoring the right parameters? You're not checking. I mean, if you use COD, chances are that it's always going to be a good measurement. But maybe you're tracking NH4 and you should be tracking NO3, but you've installed this 1,000 sensor for a good amount of money. Can you afford to change all of them just because it turns out it wasn't the right parameter? The good news there is that there are some sensors which are looking at a wide range, namely, for instance, the spectroscopic sensors, which can allow you to be a bit less targeted. But that comes at a cost, which is that if you take a spectroscopic sensor, it needs a lot of maintenance. So you need to backwash it, you need to check it regularly, to unmount it and remount it, and to check if it's still good, because we are dealing with wastewater. It's not very clean. It is full of stuff, big suspended solids in the best case, or floating elements which directly come from our toilets. Just to say, yeah, it's not that easy. And finally, what about the parameters which are harder to measure inline? I mean, BOD5 is called BOD5 for a reason. You take a sample, you put it in the lab, you let it age for 5 days, and after those 5 days, you get a result. That's not something you can measure in line. There are some tests and some sensors which now come to the market which are aiming at measuring BOD, but it's still a proxy which is trying to replicate what's working in the lab. So all of that to say that it's not that much of a given that adding sensors in your network will solve your issue. So I still have my open question. Is there a better way? Well, let's go back to our map. We still have these 2 measurement points, because those are the measurement points which are really looking at everything and making a thorough analysis of your sample and telling you everything which is inside your water. But what I didn't show here on this map is that when you think of it, there's much more on your network and there's much more in your plant. If there's a pumping station somewhere in your network, you will always be measuring pressure and flow. Sure, it's not COD and NH4, but those sensors are existing. They are sturdy. They are working for 20 years. You know exactly how to handle them. And same happen in the plant. You have flow meters a bit everywhere because it's needed for your process. You have dissolved oxygen because it's needed for your process. You're measuring pH because you might have to correct your pH. So all of that is already existing. Your turbidity is measured before and after your clarifier, just because your clarifier is here for the sake of reducing your turbidity. So all those parameters are already there. You don't need to invest anything more. Those sensors are existing. You are operating them. You know how to operate them. So now the question is, can you make better use of those sensors so that you leverage what you have? You add a lever and a new layer of information on top of that, and that way you're good to go for the next decade and for the next 100 years. Well, actually, let me spoil the rest of the presentation, as you would expect from all this introduction. Yes, you can. You can actually take basic sensors, temperature, flow, pH, dissolved oxygen, ORP, turbidity, conductivity, you name it. I mean, those basic sensors. And with help of new technologies, you calculate or you predict the other ones. You calculate COD, you predict NH4 over the course of the next 24 hours, over the course of the next 10 minutes. And that is what it's all about. It's using existing data to build what you need to operate your plant. And that's what we call soft sensors. Soft standing for software, so software sensors. Basically, to go towards these software sensors, we have a 6-step approach. The first approach is to pick an industrial site. That's what we did for the proof of concept, but that could be your plant, that could be your site. And there to gather this basic parameter. So basically, we look at what is existing, what we don't need to add within the plant to really leverage the existing. Ideally, you have a data logger existing, which means we can reconcile data of the past years. That's what happened on one of the pilots we did. And on the other pilot we didn't have a data logger, so we started from scratch, and we found out that with 8 weeks of data, we can already have something very accurate. So that first step is about gathering data. The second step is to pre-process that data, because you might have some outliers. I mean, the day you were washing your sensor, you didn't fully recalibrate it, and that day it gave a strange peak. That's not the things you're looking at, so that you can correct it. The third step is to select the appropriate machine learning technique. Might be machine learning, might be process modeling. It turns out that machine learning is a bit faster to react, is a bit more reactive. So according to our test, it looked like machine learning would be a better suit, but still there are many different machine learning techniques. Then you developed the software sensor and you train it with training data. Then you validate it, which means you take that soft sensor base and you see it over time in your plant to check how that works and how that is going to help you on the long run. And actually, the sixth step is to take the output of the soft sensor and to integrate it into your operation, be it in the plant automation or be it as an advice and in operation. It's important for me here to make a disclaimer and to be very transparent. We are, with GF Piping System, an expert when it comes to piping systems, actually, to hardware and what's next to the hardware. We are not a process company, and we don't intend to become a process company. So here, that sixth step is outside our scope. It's not something we intend to do in the future, and it's not something that we do today, which means we feed our data, we feed those elements to the EPC, to the OEMs, to the plant owners, to the plant builders, so that they can leverage this data. But we don't intend to steal any portion of that business from them, because just it's not our job, it's not our core expertise. But that is an integral part of the six-step approach, because if you're taking data in order to do nothing with it, it's a bit of a pity. So I was just putting it here as a reminder that we want to make something with this data, but that's not something we do. So let's dig a bit deeper into those steps. And let's start with the data acquisition. I shortly alluded to, we were running 2 pilots in industrial parks in China, just because we were working on a parent project. I'm not entering in the details of the parent project, but what we were looking at with the parent project was how can we leverage stream synergies? If you have one stream which has a pH of 4 and one stream which has a pH of 10, can we mix those streams in order to reach a pH of 7? Not going into the details. If you want some information of that, I will be very glad to exchange with you after this conference. But just because we had those two industrial sites up and running, we had built what you see on the right hand, which is a non-premise cloud platform. So basically a cloud platform, because from everywhere in the plant you could access that cloud, but only accessible from within the plant for safety reasons. And on that cloud platform, we started gathering data. So basically, we were leveraging the existing hardware, taking the outputs of pH, of flow, of pressure everywhere in the plant, driving that to this online platform. And in this online platform, we were putting a timer so that we were always looking at the past. So 24 hours in the past. Again, for safety reason, it's an industrial park. On an industrial park, if there's one thing you want to avoid on the pilot is to disrupt anything that might be happening on the plant. And we were adding on top of that lab analysis, which was done by the operators of the plant. So basically COD, NH4, NO3, they were drawing samples, taking them to the lab. In the lab, they were analyzing the samples, and the result of all of that was put on that cloud platform, so on-premise cloud platform. So that was our data acquisition. And once we had that done, we were processing that data. So here again, what you see on the right hand is really an illustration, because for safety reason, I cannot show you the actual data. So it's a bit simplified, but that is to enable me to show you how that works. Basically, you have the curve on the top, which is what's really happening. Let's imagine that's our curve of COD. What we do is that we take that curve and we break it down in 3 other curves. First, the trend. So that's the first very simplified curve you see. The second is the seasonal. So here you're looking at a pattern which is repeating. Usually the seasonal goes over 1 day. So on an industrial plant, it's always 1 day. I mean, it's really every day the same. On municipal plants, it's slightly different because on municipal plants, you also have this element of seasonality in the sense that your plant is not behaving exactly the same way in winter than it does in summer. Might be a bit less the case in countries like Singapore, where temperature doesn't go as low than in Europe. But as soon as you have temperature variation, I mean, we're working with living bioorganisms, so there's a seasonality. And finally, the last graph is the residual. So it's everything which you need to add or subtract from the 2 others to find the observed data. So the residual is really the one where you can play with. We have to understand what's happening aside from the trend and aside from the seasonal. So once we had pre-processed our data, we were looking at selecting the appropriate machine learning technique. As I shortly alluded to, we had a look at modeling, but we thought modeling is probably not what we need for the sake of that project. Might be interesting in other cases, in other time scales, but here we were looking at something which had to be reactive and fast moving, thus machine learning. So we had a look at several methodology for machine learning. I'm not going to try to sell you I'm an expert in machine learning. I'm by far not, but we had a look at various different techniques, and we found out that the feed-forward neural network was a good one. And the reason why it's a good one is that it is a simple one. It is one which gives you an accurate result while not being overcomplicated, which means you don't need to have like 30 inputs and a supercalculator to come out with something. You can go down to 2, 3 main inputs and some correlation matrices, and with that deliver you the output. So basically what you see on the right hand is the functioning principle. You have an input layer, so that's our sturdy basic parameters, again, pH, flow, and all of that. You have the output layer, which in the case of our experiment was COD, NH4, NO3, and the hidden layer is the rules which we identify, which are translating one into the other. That can be direct rules, or that can be this correlation matrix I alluded to. It's important here to say as well, we didn't start from scratch. There is a record of almost 20 years of research of various researchers which have been looking at that field, and we were clearly standing on their shoulders. So especially if there's one paper you want to read of that subject, I recommend you the paper from Jaime and al. From 2012, which was looking at very different ways of using these software sensors. And they came up with recommendations with regards to which one is the best. So just to say, that's how we selected the FFNN, so the feed-forward neural network. Then step 4 is to train the soft sensor. Training is exactly like it is. Imagine our sensor like Rocky out there with the nice pumping up music, and that sensor is fed daily with the input of our training data. So in one case, that was 8 weeks of data. In the other case, it was 2 years of data that we fed and fed and fed and fed for the soft sensor, so that he started with this machine learning to recognize patterns. When that happens, then this happens. When that occurs, then that's the output. So that's what we're looking at in this training phase. And again, we try to see the trend, we try to see the seasonal, and we try to see the residual. And for the residual, what we are doing, which is a bit special, is that we take all the parameters and we feed them into a matrix. And what we're looking at here is there one or two which is more important than the others? And what we found out in both sides is that every time we had 2 parameters which really stood out, which had a strong correlation with COD, NH4, NO3, a third one which had a minor correlation, and all the others which were almost noise. And what's interesting here as well is that for 2 plants, those main parameters were not the same. So for one, it was a combination of flow, dissolved oxygen, and pH as the third one. And for the other one, it was pressure on some lines, flow again, and conductivity. So different sets, but it's almost a rule. You can usually find 2 to 3 main parameters, and then all the other ones, if you have them, you're going to be a bit more accurate because you can build that matrix. But if you don't have them, you're not really going kilometers away from the rule. So that was the step of training of the soft sensor. And again, acquiring the data was 2 months. Training the soft sensor is another 2 months. Then we had the fifth step, which is the validation of the soft sensor. What's important here is that I mentioned the speed trap element with the measurement in the wastewater treatment plant. It would be a pity that our full process delivers something which is again doing pictures. So it's not. In machine learning, there's learning, which means that our sensor keeps learning over the time, which means when you start the sensor, he already has a very good accuracy, and that's why we say we go to step 5, validating. But he's not yet at his very maximum because he will keep improving over time. So we use a learning algorithm to measure the difference between the calculated output and the real output, and to keep adjusting the weight of various parameters. And here, that's one extract of the COD curve on one of the sites. What we see is that there is a clear correlation between what's the real in blue and the predicted in orange. We had on the site where we had 2 years of data, we had a 5% error. And on the site where we had only 2 months of data, we had a 7% error. If you're familiar with flow measurements, you might look at that and have big guys and like, what, 5%? That's crazy. Because in flow, the usual error is going to be 0.1, 0.5, or 1%. Well, when we are looking at organic parameters, 5% error is an absolute hit. If you're making the measurement in the lab, you are usually around this error. And if you have these drifts, which you don't see because you take one sample or 1 sample per hour or 1 sample per day, you are by far not at anywhere close to 50 or even 100% accuracy. So really, 5% error is a game changer. And if you look at actual sensor, like spectroscopic sensors, which are measuring that inline, it's also roughly what they have. But here, you don't have any risk of drift. So you really have something which is sturdy. What's important to note here as well is that I was mentioning that we try to reduce the operating costs. We try to improve these operating costs. But we don't improve the operating costs by stopping the analysis. You are not stopping the hardware analysis in the lab just because you have a soft sensor. That's not what you do. You are saving on energy and you are saving on chemicals, but you have to keep making the analysis in order to keep verifying how accurate is your soft sensor so that it keeps learning over time. But again, here, 5 to 7% error is really something, according to literature, which sounds to be good results. And according to our discussions with operationals, something that they can really leverage to become better in energy and chemical consumptions. So finally, the sixth step is to integrate the machine learning soft sensor into the automation, or at least as operation advice. As I already explained, it's clearly outside of GF scope, so that's not something we will be doing in future. Now, for the sake of the pilots, as we wanted to make a proof of concept, we integrated that into our software platform in the sense that we placed those sensors virtually on the map. So basically, you had those points. You have to imagine those points, and you could click on the point and say, hey, at that point, now I have that COD, that NH4, that NO3. And then we also had this prediction, which was saying, according to what's upstream and downstream, we expect that level to go to this within the next hour, which was quite accurate, and then giving you a trend over what we expected for the next day, and then it's a trend. It's like when you're watching the weather forecast on TV. It's not because they say it's going to rain tomorrow that it always rains tomorrow. So there's a level of accuracy which comes into play. So that being said, what did we achieve with these 2 pilot sites? Well, first, we were able to reach a further 22% reduction in chemicals used. Remember that we were within a parent project where we already could find some stream synergies and reduce the use in chemicals. Well, with this additional layer within the study, we were able to have a further reduction in chemicals. Over the testing period, the energy costs were reduced. We were not able to quantify that for a very simple reason. It's because when we kicked off the project, I was able to travel to the site. And then there was this little thing, I don't know if you heard of it, it's called coronavirus. And it's kind of changed the way that we do business. So it was difficult for me to keep collecting those data. And as long as you don't feed all the advice into the operator's daily life, he cannot really apply everything he receives. So it's hard to see a difference in energy that you can quantify. We saw clearly a reduction in energy costs, but to say if it's 20%, which is the magical number within our industry, or if it's more, I cannot tell you today. If we have the same discussion in 6 months or in 1 year, I will have a relevant set of data which will enable me to tell you what we can reach here. So just for you to have an idea what we're talking here about, literature, again, coming from various places in the world, provides you with this roughly target of 40% reduction in operating costs and with welcome side effects. Because, of course, we've been focusing on the cost because that was our first aim and because we are not operators. So we were able to see this decrease in energy, this decrease in chemical use, but there is an obvious welcome side effect. Your biology is never going to be upset anymore, because it's not like one day it's starving because it doesn't receive anything and the next day it's overloaded with stuff to eat and everything for the bacteria. You really can smoothen that. And if you smoothen that, that means that your plant, which was designed to overcome the upsets, now doesn't have to cope with the upsets. So you can surcharge your plant and bring more load on your plant and more hydraulic capacity. And that is especially important when you think of countries like Singapore, because Singapore's plants have been designed for a certain level of population and a certain level of loads, which lasts from some decades ago. And all this revamping wave we currently see in Singapore is partially because you need additional capacity. So now imagine that software will be providing you this hardware additional capacity. That is a fully other scale of savings. You just don't need to invest in new plants or less compared to the existing. So just to say, there's the primary focus, which is OPEX reduction, but there's also a cool story beyond that, which is that you're working more with nature and less with chemicals. You are treating higher loads. You have less bad surprises as operator because your biology is all of a sudden very upset on a Saturday evening. So just to say, there are a lot of welcome side effects. And therewith, that brings me to my outlook and to my conclusion. Future might be complex. That was my introduction. But future will always be building on the shoulders of the present, which means if we are leveraging the right, simple, sturdy bricks, we have all the Lego pieces to be building the future. And exactly like YouTube needed to be a video dating site to find out that one day they would become what they are today, exactly like Spotify needs to put up some music from some unknown band somewhere in the middle of nowhere in order to find out the new hits that are going to be the ones that everybody's listening to in the future, exactly like Instagram had to be bourbon and to offer you a full set of useless features in order to find out that people wanted to share pictures. Exactly like that, you need to leverage what you have, flow, temperature, pH, conductivity, to be the bedrock of data, which is going to help you in the future to overcome the new challenges that are still to come. And that's true for the next 5 years. That's true for the next decade, but that's also true on the longer run, because you never know what will be the challenges of tomorrow. And now, last but not least, just a last thought. Chances are that within this presentation, hopefully not because I was so interesting, but I have to be realistic as well, but chances are that you watched your smartphone 8 times. and we are watching our smartphone in average 150 times per day, we react to an SMS within 4 minutes. How can it be then if my wife is sending me an SMS saying, "Where are you?" I'm answering straight away to tell her I'm in the garden. And how can it be that I still expect to have processed data giving me a number, and hopefully if it's BOD5, I react within 5 days, and maybe if it's BOD21, I react within 21 days, and I'm doing something. How can we build, I mean, I'm taking out two extremes, but how can we build this reactivity element within the way we operate our plants, and how can we leverage technology in order to be much more reactive, efficient, and on the long run, how can we be better as operators? And that is my conclusion. And therewith, I leave you to the question part, and I'd be glad to take any questions you may have.
Thank you, Mr.
Antoine.
Walter. Now we come to the Q&A segment, which would be moderated by Ms. Christine Yap, Sales Engineer of George Fisher Water Treatment. Ms. Yap, the floor is yours.
Thank you, Lily. Hi, thanks Antoine for insightful sharing on how to optimize our plant operation using the soft sensor. So on the floor, right, currently we have question from Mr. Sanjeev, NUS. He's asking, if we know the process so well, then we will just need to figure out which parameters need to be monitored, and then we'll use it. We'll use it using the model base rather than the database. So what is your view and suggestion on this?
That's an excellent question, Sanjeev, really excellent question. It's an excellent question because we are really touching a nerve here. It's also an excellent question because we had ourselves that same question when we started. So I'm somehow patting me on the back and saying that's a good question as well. But what's important here is that models are incredibly powerful, and they can, if you're, for instance, building a digital twin, then most probably modeling is even stronger than machine learning. But we have to look at what we are aiming at. If you run a plant which you expect to be within the same type of conditions over the next decade, then probably modeling is a better bet because it's not going to move and you can really leverage that. But if you expect, if you're in an industrial process, for instance, and you expect, well, today we're building that, today we're producing that, tomorrow we might be doing something fully different. Each time your model needs to be reprogrammed, needs to be changed, needs to be adapted. That's not the case with machine learning. Machine learning, within a certain time frame, will understand that there's something different. So that's the first answer. The second answer is, it's a question of reactivity. Sometimes machine learning will give you a hint as an operator in a time frame where your model is just starting to compute. So that might not be something you need if you're a pure municipal plant, because if you're a pure municipal plant, what really can happen in terms of drifting is all of a sudden there's a blockage on the sewer, or today, because of a traffic jam, people came home 20 minutes later or earlier compared to a normal day. But if even a part of your network is industrial, you can have all of a sudden, I mean, one batch is over and is just discharging, or there's a problem and they had to stop and they are discharging. And there you have to be very reactive because we are talking of very low I'm French and I'm moving too much. I'm going to move less. But if you are able to be more reactive, you can isolate that additional stream and you can build on it and treat it with a different way. And so machine learning gives you much more agility and flexibility. So just to say, the two techniques are good techniques. We just thought that if there's an industrial compound within your reach, you probably shall rather go to machine learning. And sorry, that was a very long answer.
Hi, Mrs. Andre. I hope this answered your question. Moving forward, we have another question from the floor asking for based on a pilot plan in China, exactly roughly how long does it take to complete the 6 steps approach?
So we have two cases. The first case is you start from scratch. If you start from scratch, then you need to start by gathering data. So as I mentioned, gathering data takes roughly 8 weeks. So that's, let's say, 2 months, 2 months of gathering data. Then you train the sensor. That takes you another 2 months. In between, you have a cleaning up of the data, but the cleaning up of the data, you can do it as the data progresses. So let's say it doesn't impact the timeline. So it's 2 months plus 2 months. After 4 months, you have something which can be validated. And then after these 4 months, your soft sensor is delivering you really powerful outputs, and it's going to be always better with time. The shortcut is if you already leverage existing data. If you already leverage existing data, then you can shortcut the first 2 months and you just need this training time. And if you just have the training time, so it's 2 months. Let's say it's between 2 and 4 months to complete the 6 steps, or at least the 5. As I said, the 6th step has to do with integration within the operation, which is a bit outside our reach.
Okay, see. So Antoine, we have follow-up question from Mr. Sanjeev. He's suggesting why not to take a hybrid approach to get the best of the both worlds.
Actually, Christine, if you don't mind, I will bridge that question with the question from Jasvinder, which is asking also what is the main criteria when selecting the suitable machine learning, because you're going to see that those two come together. Sanjeev, you're fully right. We could be combining, and you can always do more. There's always a way to do more, and some of the machine learning techniques I was referring to are more powerful than the one we used. But at a certain point, it's a balance between additional effort, additional costs in terms of which kind of data you need, which kind of computing power you need, and additional benefit. So maybe that if you combine both of them, maybe you can reduce your accuracy from a 5% error to maybe a 2 or 1% error. But the thing is, when you're operating a plant, a 5% error on COD is really peanuts. So you can do better, but you don't really need to do better. Now, it's fair to say as well that that's what I said today in 2021. Maybe our computing capabilities will be so high in 2026 or in 2030 that it's going to be a no-brainer, that you can go for a much more advanced machine learning combined with modeling, and it's going to work absolutely like a charm. The fact is that nowadays, I had to take one computer instead of the other, which I have in my office, just because one of my computers wasn't able to run Cisco WebEx. I'm just saying we are still at a level where sometimes the capabilities and the expectation we have from the technology don't really fit with the existing hardware. So we have something which is good enough. And you're right, we should always aim for better. And that's why it's not a picture, it's a movie. It's developing and it's going to keep developing.
Okay. Moving on to the last question from Mr. Harris. How relevant is your AI approach in the developing countries where labor is still cheap enough to deploy and to take the manual measurements constantly?
It's another excellent question, which is one of the root questions we had when we started our parent project in China, because I know there are countries where manpower can be even cheaper than in China, but already in China, we are not talking of the level of manpower cost than we have, for instance, in Switzerland. And actually, manpower is one element of the equation, but it's not the full equation. When you're doing the manual measurements, It means you draw a sample, you bring the sample to the lab, you do the analysis in the lab, and depending on the methodology you're following, there is a time. Again, if it's BOD5, it's 5 days. If it's BOD21, it's 21 days. And that is not something you can compress. So it might be cheap, sure, but it's not providing you with the speed and the reactivity. So that's what you will be missing. So that's why we were quantifying in the project in China how much you save because you're reducing chemical use, you're reducing energy use, and how much it costs additionally, because now you have one data logger in the plant, you have one cloud platform, which is software based, so it doesn't cost a lot, but still you have to consider that it's in a data center somewhere, that you have to build in some safeties. And even in a low cost country, it was a no-brainer. It's really a no-brainer, because if you save 5 or 10% on coagulant and flocculant, if you save on methanol you have to add to your biofilters just because you weren't able to control the curve of nitrogen the way you wanted, well, already that was worth it, aside from all the other welcome side effects that you don't need to invest into revamping your plant because you have a better hydraulic capacity and so far and so on. So absolutely right. It's a legit question. It's a question we are still asking ourselves as well. But in terms of pure cost, it's already, I think, well balanced. Now, on top of the cost, there's also a question of qualification, because, I mean, in my engineering school, I was told how to do all these analyses. I learned to do those analyses, but even though I hope I still look young, my engineering school is now almost 15 years ago, and put me again in that same lab. I have no clue how to run an analysis. And still, it's not like I went to sell insurances. I'm still in the water industry. So it's not a given to make those analyses. You need to know what you're doing. You need to take your samples in the right way, not to contaminate your samples. You need to have the reactants, the materials, and everything. And that's beyond the cost. That also raises a question of competence and capabilities.
Okay. So, Antoine, the one last question from our floor. Apart from the wastewater treatment plant, right, do you have any experience using AI or soft sensor application in the water treatment plant operation?
Well, it's an interesting question. I will have two answers to that. Our project was on wastewater treatment. Now, within what we did, there's nothing which indicates that it has to be on wastewater. Basically, on drinking water, it's going to be different parameters. You will probably not be looking at COD. You will be looking at different kinds of indicators, but still, you can reconcile them exactly the same way. So that approach really works, whatever the field. First important thing to note here. The second, if you want to go a bit more in depth, and just to tell you that we are really agnostic when it comes to that, and that I have no special push here to tell you I want to sell you one solution against another. I have the pleasure to host a podcast which is called Don't Waste Water, which you can find on all the podcast platforms, and you can find on my LinkedIn as well. And I interviewed a couple of weeks ago the CEO and founder of a company called Storm Harvester, and they are actually applying the same type of methodologies to the sewage networks, so pressureless networks, to manage the to manage the sewers overflow, to better manage the presence of water in cities, and to better manage the storm tanks. Just to say, similar methodologies, kind of different area, and it works exactly the same way. So that's the beauty of it. Once you've understood and integrated that gathering this bedrock of data just opens any possible doors, then the only limit is your creativity and your imagination. You can really apply it to any kind of water-related field.
Okay, once again, thank you, Mr. Walter and Ms. Yap.
Yes, sorry.
Sorry.
Just one last thought.
Okay, sorry.
So I was I'm really sorry to interrupt you, but
It's okay. I'm sorry to interrupt you as well.
there was also something which is kind of trending those days, which is wastewater-based epidemiology. And those exact same methodologies are the same we now use to track COVID in wastewater, and even to track COVID in the air. So just to say, what's important is to understand that there's a bedrock of data, and then from that bedrock of data, you can even have a better way to understand which part of a city is suffering from COVID right now and which one is pretty free because they got vaccinated earlier and so far and so on. But I don't want to go off topic here, just to say that that is also a trending topic and a reason for people to look at that right now. And that being said, I stopped being French, I stopped talking.
Okay, that's all. That's it, right, for the Q&A segment. So now, once again, thank you, Mr. Walter and Ms. Yap. We look forward to all to attend our upcoming webinars. Thank you all for your participation. Please contact SWA Executive Office and George Fisher for any further query. Stay safe, stay well. Goodbye.